Okay, please go ahead.
Thank you. Good afternoon, everyone, and welcome to this session on construction and building materials. The construction building sector uses a substantial part of the collective new natural resources and is also responsible for one of the major waste streams, where any step towards resource efficiency and circularity are of huge importance. So in this context, we talk of different types of materials like inorganic and organic, heavy and light, or very complex to actually very simple ones, with different concerns when it comes to potential harms and risks, logistics, management, technical challenges, and so on, but also different possibilities. So this afternoon, we will listen to 6 initiated and experienced researchers in this area, who hopefully will shed some more light and optimism on our future. And I will also encourage you in the audience that you really are on your toes while the speakers give their speaks, and put any questions you might have in the chat, since we will have short questions and answers after each talk, instead of this joint panel discussion that has been in the other panels. With this very short and brief introduction, since you're not here to hear me babble, I think we get started. And our first talk will be given by Martijn van Praagh and Linus Brander, who is actually myself, and is titled Obstacles and Promoters for Use of Secondary Materials. So Martijn is R&D manager at AFRY, and is also a part-time lecturer at Center for Climate and Environmental Research at Lund University. And myself is a senior scientist in geological materials at RISE. So with that, please go ahead, Martijn.
Thank you very much. Can you hear me loud and clearly?
Yes.
All right. Thank you very much, Linus, for this introduction. I'm very glad to be here, and I'm looking forward to the other presentations. So our project, Obstacles and Promoters for Use of Secondary Materials in Sweden, was a strategic project in the Resource Innovation Platform. And because you can imagine that use of secondary materials, even if you delineate it to Sweden, is a wide field, we further delineate our project and focused on ashes and recycled concrete in construction. And apart from Linus and myself, also Lena Smuk, who was formerly at RISE, had a large part in this project, which ran from 2018 to 2020. Now, Resource, for those of you who have not been in contact with Resource before, is one of Sweden's strategic innovation platforms, or SIPs, as we call them. And Resource focuses on promoting research and innovation leading to sustainable use of materials. And that might be on any scale you might imagine. So it might be on an atomic or molecular scale. I have some background noise here. I hope you can hear me. From a small scale to large scale, and our project focuses on recycling of materials. So the rationale and the starting point of our project is resource depletion, or the use of if you want, virgin materials, which especially if you measure it by ton per year, most of which is going into construction. The question was at the start of our project, and still is, of course, so what potential do we actually have when we take into account reclaimed resources, which I think is a better term than secondary materials, which potential do they actually have to substitute for virgin materials? Is it this much? Is it this much? Or is it even more than that? What we did in our project was that we looked at obstacles and promoters, which might be policy, financial or fiscal instruments, regulations, technical regulations, environmental risks and environmental regulation on the one hand, business models, logistics, and so on the other hand. And we try to identify where are the main stopgaps and where do we see promoters which we might use, or even make sure that they are capable of making the increased use of reclaimed resources fly. So how did we go about? This was quite a interactive and collaborative project. I just want to draw your attention to that we conducted our project mainly through assignments for which we recruited experts from the resource competence database, and we had these experts conduct parts of our project. And not every step within the project, but quite some parts of the project were interactive activities with stakeholders from the recycling industry, from the construction industry, and also from municipalities and authorities in Sweden. And these were partly interviews, deep interviews or surveys, and then also workshops where we collaborated directly with the stakeholders. Most of these assignments, they led to reports and results, which we then analyzed and used to come to suggesting solutions on a strategic level on how to remove stopgaps and how to increase the efficiency of promoters for use of secondary materials or reclaimed resources. And those reports for the assignments, they are attachment to our final report, and you will have the link to our final report at the end of this presentation. Now, analyzing those assignment reports and the results from our project resulted in 38 suggestions. You have to think about it as suggestions on a strategical level to stakeholders in 6 different categories on how to get rid of stopgaps and how to promote the reuse of reclaimed resources. And then we subjected these suggestions to a peer review, which means we both interviewed and had a survey where peers, stakeholders, and experts had the possibility to grade those suggestions. And those 6 categories we used are these you can see here: roadmap, end of waste, business models, knowledge and expertise, technical regulations, and then national strategy for resource efficiency and instruments and policies. And the reason that those last 2 are not as colorful as the other ones you can see here is basically because of those 38 suggestions we proposed, none in those 2 categories made the top 10, which I want to show you now. Just briefly, the peers had the possibility to grade our suggestions and of course to comment and to make free comments or to comment on specific suggestions. And you can see here, those suggestions, the top 10, which were graded as very good or good and scored the highest. You can see on the left-hand side here. There is a slight bias towards knowledge and expertise, which is the green one. And there's also a slight bias towards technical regulations, which might be a result of that. There were a lot of technicians and technical experts involved in our project. So these 10 suggestions scored the highest and were really appreciated by all the peers. And one I want to put a little bit extra stress onto now and draw your attention to is actually the last one, which scored the highest, which is called which is in the category road to end of waste, and it's called large scale pilots. And this is basically that we still in 2018, and this is still true, we have a lack of large scale projects in Sweden, construction projects where we on a large scale use those reclaimed resources and then gather information about product development, about environmental risk assessment, about lessons learned, and feedback those results into removing our stopgaps and to developing our promoters for reuse. So before I end my presentation, I of course want to acknowledge everyone that was involved in this project, quite a lot of people. Especially, of course, the participants, the peers, the experts participating in the workshops, our assignment project managers, and a lot of more people, which you can find here. Also, I have, of course, to acknowledge the financial contribution from the Swedish Waste Association and Energiforsk. And then I want to, last but not least, draw your attention to the final report, which is freely available on the resource project database. And of course, I open the floor for questions now, but if you have any questions after our session or later on, please feel free to contact me or, of course, Linus about the project. And maybe questions about ashes to me and questions about concrete to Linus. Thank you.
Thank you, Martijn, for that very interesting talk. And you also kept the time very well. I don't see any questions in the chat, but one thing I think of is this project ended a little bit more than 1 year ago. Have your thoughts about these conclusions changed in any way or developed since that, and in which way?
That's a very good question. And almost as if we've planned this, we had the discussion before, Linus, you and I, about, okay, what can we say more than 1 year later? Are those suggestions still relevant, we gave? And well, one important thing is, of course, that just, I think about a week or 10 days ago, the delegation for circular economy in Sweden, they presented a report for the Swedish government where they suggested the most important steps towards a circular economy in Sweden. And if not inspired by our project, at least you will find parallels and parallel suggestions in that report to the Swedish government. But when it comes to ashes, I think two important things I want to stress, which are at least as relevant as they were in 2018 and 2019, that is that we have to develop environmental risk assessment in lieu of circular economy. We have to have better tools to see, well, which material streams do we really have to divert from our circular material streams? Which can we toxify or should we toxify? And which can we use as they are or with relatively little adjustment? And the other thing, if you think about, for example, life cycle assessments of reclaimed resources in construction projects, a little bit depending on where you put your borders for your life cycle assessment. Normally, one factor that sticks out when it comes to environmental impact is the carbon dioxide equivalent emission due to transport, because we're talking about heavy materials, both ashes and concrete, and well, most of the construction material. And that also means that we have to put extra stress on how can we solve this use of resources on an urban or a regional basis. And about concrete, I think you are much better equipped to.
Yeah, I jumped from my moderating role here to short presentation role. Like you said, Martijn, and as you see in the audience, these from the concrete point of view, I think these 4 bullet points pretty much summarize how I view it. I still think that national end of waste criteria, or even more now, are very important to develop to aid the recycling of inert masses to benefit of all involved stakeholders, not only the recycling companies or the waste owners, but also end users and potential buyers, to lessen the confusion about what's allowed or not, and increase reliance in this material. And also end of waste criteria is based on best practice and pilot cases would also give municipalities and like the Swedish Road Administration the right knowledge, enabling them to requesting recycled material in public procurement of roads and buildings and so on. Another important issue is the sustainability parameters, where we have seen that sometimes if you only look at climate in your environmental budget, you risk to demotivate the recycling of crushed demolition concrete. Since if you can reuse a concrete structure, you will gain both when it comes to climate and when it comes to resource efficiency and management of resources. But if you can't reuse it, and okay, the next step is of course to recycle as new aggregate in new concrete, for example, then you don't gain, so you mostly not gain anything in the climate or decrease in CO2 equivalents. So if you're only looking at that and not also consider circularity and resource efficiency, this could be a demotivation. So it's very important Yep. I don't think I think that's pretty much summarize it. I think we are placed for one question from the chat. We have one from Lisbeth M. Ottosen. Should we not focus more on reuse than we are doing currently, rather than recycling? It's a little bit on what I was into answering, but maybe you have something there, Martijn.
No, I absolutely agree that if reuse is possible and feasible, then we should focus on that. But like you said, Linus, it's important to try to have an holistic view on sustainability and be very clear about the sustainability parameters that you include before you take this decision. But normally you could say, if I can reuse, especially if I can reuse at the same location and thereby avoid a lot of transports, I think then reuse will normally always come out the better. But it's also very important to remember that those are not they are not mutually exclusive, or they are not antagonists. I think, especially if we want to reach a circular economy, reuse and recycling. Recycling is the pathway. I think a part of the pathway to a circular economy.
Yeah. Good answer. And I can only add to what Martijn said, that it's of course important to have this holistic view. And for example, when dealing with a building from the concrete perspective, you should do some kind of mapping or exploration of building stock to see, okay, can we reuse this? But in some cases, when it's, for example, concrete casted in place and so on, the efforts to take it out and reuse it might not always be beneficial. And then as second best, you need to consider recycling. Great, thanks. Good to see some activity in the chat. Hope for that for next talks. Thank you very much, Martijn, for presentation. I think we skip to next presentation, which is on a completely different materials, and it's actually one of my colleagues from RISE that will give this presentation, Anna Jansson. Anna is a PhD and a research scientist at RISE and has expertise in recycling and durability of plastics, and will give a talk titled Recycling of Plastic Pipes in Large Scale. So Anna, yes. Please, the stage is yours.
Yes, I will share my screen if I can find the right to find presentation first. Select. Okay.
Now we see your screen.
Now you see it, and we go to presentation mode. Fine. There you go. Thank you for invitation. Invitate me to present this project. It's called Repipe Demo, large scale collections.
I'm sorry, Anna, you're sharing the wrong screen. We are seeing your kind of.
Stop share. Still the wrong screen?
No, you're not sharing anything at the moment.
Okay. Okay. Share screen. There you go. No. And share. Now.
Yes.
There you go.
I think that's right.
Yeah. And the slideshow. Now, you still see.
Adjusting. Okay. Again. Can you see take from the top the change the switch the screens. It's on the top of your screen. Should be one of those buttons, because we are seeing now your
yeah. Okay. On top, I should click.
I think is it V standing? I'm sorry, I don't speak Swedish myself. So.
Is it visningsinställningar?
Yes, you should be able to swap the screens.
Yep, there.
And yes, yes, that one. Yeah, yes, that one.
Good.
Yeah, now, great. Now,
finally,
great.
Sorry. Thank you for inviting me. Now, the project I'm going to present is called Repipe Demo: Large-Scale Collection, Sorting, and Recycling of Pipes. It's a 2-year project, and it's funded by Resource. It's a demonstration project where collection of pipes should be demonstrated. So it's a large number of participants. You can see them here in the slide. It's about 30 participants, and the research was performed mainly by Chalmers Industriteknik and us at RISE. And we have the whole value chain from wholesale, subcontractors, construction companies, transport and sorting companies, material recyclers, pipe and profile manufacturers, clients, branch organizations, and others, which is a raw material producer and manufacturer of grinding equipment. The background is a previous project also called Repipe, and it was a research project. They estimated that 5,000 tons of pipe residue material was produced every year in Sweden. And the main part of pipe waste is incinerated today because it ends up in combustible waste at the building site. And the pilot project demonstrated that it was possible to produce new pipes from this residue material, and the quality was good. So in this project, we should upscale this and do it in full scale. Very easy on the paper, but not in real life. And the nice thing in this was that we had a final customer, a preschool called Hoppet, and it should be as fossil-free as possible. So we should move from a linear system of material use to a circular one. This picture I borrowed from another project called Rebus, and we can imagine that the factory you see in the picture is a pipe factory producing pipes for a building, a new construction, and the building finally is renovated and demolished eventually, and new pipe waste is then formed. The waste is collected and should ideally go back to the pipe factory and become new pipes. Today, much of it is incinerated, in Sweden at least, and in other countries maybe landfilled. If we close the loop, the material goes back to pipes, or it can also be an open loop, and then you have other projects made from this material. The demonstration is shared by this picture, and we go from the left to right. We start at a place for collection, which could be a construction site, a wholesale subcontractor, and it's collected and picked up by a waste collector, sorted at a sorting company, recycled, upgraded by a material recycling company, sold to a pipe manufacturer, and finally on the market, and in this case for this preschool. The goals of the project is to demonstrate pipe collection and to gain increased knowledge about incentives and how to work to increase collection, and possible and effective logistics concepts. To do this, we have a lot of challenge. To the left, you have the challenge of volume and economy. Plastics waste doesn't have a large market value, And you also have volumes. Sometimes you have quite small volumes, and it's difficult to get economy to send it to recycling. When you come to sorting and material recycling, you have the quality issue. You have to sort very carefully. You have to handle the material so it doesn't become too contaminated. To be able to make new pipes with quality that the market wants. If we start with the collection, where the waste is produced, the focus for most construction companies is to minimize the waste, of course, which is good. Practical solutions is needed. Usually there is a lack of place to sort the material. Where do you put the container? You have variation in amount and size of the waste. Pipes come in different shape and sizes. We also need clear instructions and in different languages sometimes. It's very important to have a communication with the waste contractor, what type of carrier to use, when to collect the pipes, etc. To know in the construction where does pipe waste fall. The craftsmen and women, they want feedback. What happens to the material that they collect? Is it recycled? The collection places can be very different. We had a large number of drilling companies in the project, at least their organization. They operate in many places all over Sweden, and they drill for water and geothermal heat. They have a very clean waste stream, the same type of material, you see it in the picture, but it's very small amounts. And if you see in the map, Sweden is a long country, so the map doesn't even fit in this slide. And the brown bullets, you can see it's the recyclers, and it's very difficult to find an economic way to collect it and move it to the recyclers. And then we come to logistics, the waste contractors. The market price for mixed plastic waste is about 200-300 Swedish crowns per ton, and that does not cover the transportation cost. So maybe you should think just cut the pipes into small pieces, shred it. Well, that's what the waste contractors also say. Could we just shred it? And then the sorter says, no, you can't, because then we cannot sort it. And to be able to get the right quality, the pipes need to be hand sorted by trained staff. And so they have to transport the pipes as they are. But during this project, we had the new legislation saying that plastics waste must be handled separately and sorted separately. And also the incineration tax increases gradually. So the scenario might be different in the future. So we have made some calculations on how long you can transport a truck with pipes, and just a few 10 kilometers. And it's not possible to transport from Stockholm to Göteborg. The distance is too long. And as we move forward in the chain, we come to the sorting companies.
Sorry, Anna, you have 1 minute.
Oops, yes,
Yeah.
I have a few. Yes, and as you see, it's bulky material, and it's handled by machines and then hand sorted into 4 different materials. Then it's grinded and pelletized. And in this project, we lacked capacity of washing. But now a company called Van Werven, established outside Borås, has this facility. Well, did we get any pipes for the preschool? Yes, we did actually. With a lot of trials by the pipe manufacturers in the project. And as you can see in the picture, finally they got a pipe marked with PE hoppet. And up to the right, you see a pipe with the bad quality. It was contaminated by metals. And it was allowed to make drain pipes for outdoor use. And here you can see the construction site and the pipes to be installed. And in the container, the blue one, this construction site, of course, collect pipe waste. And thank you for listening, and keep sorting your waste. 10 minutes fly.
Yeah, it flies. Thank you very much, Anna, for this very interesting presentation. I think we actually have time for one question. One from Martijn. Can't the sorting be automated?
Yes, we actually had a company with automatic sorting equipment, and talking to them, they said, well, yes, it's up and running, but the pipes, they are round. They are just rolling around on the conveyor belt. So that makes it difficult. And if you shred it, the pieces are too small. But in the future, there are machines nowadays that can sort very small pieces. So maybe in the future, but for now, it's hand sorting.
Okay, thank you.
That works.
I actually had a personal question. How do you manage to make 32 partners to work in the same direction? But maybe you can answer that by writing a handbook for our project leaders.
Yes, I would say it was very, very difficult. Some of them are very used to work together. We have been working with them for many, many years, and we trusted each other. Some of them were new, and some did their share and some didn't. So it was, yes, it's a challenge, yes.
Yeah, thank you very much. I also want to, for you that haven't seen, Angelica has put the links to the report, the resource reports in the chat, both to this project and the previous.
Yes, I'm actually writing the end report. So this report will be handed in next Friday, so it's not
this is from
the final report. Yeah. Yes, it will be found. Yes.
Thank you very much.
In a short while. Thank you.
Yeah, thank you very much. So now it's time for a third presentation, and it's by Professor Patrick Teuffel, who will give a presentation titled Bio-based construction materials during service and end of life in a circular economy. And Patrick is Professor of Innovative Structural Design at Eindhoven University of Technology. So please, Patrick, the stage is yours.
All right, thank you for the invitation and the introduction. Yeah, as mentioned, I want to talk about bio-based construction materials, and I will present briefly two projects, one small project which we finished already, and a larger project which we started last year. And in the first presentation, we already saw a similar diagram, basically indicating the big impact of the construction industry in terms of the use of natural resources compared to other industries. And of course, on the one hand side, it's a big responsibility to improve that situation, but on the other side, I think it's also a big opportunity and chance to do something good in that context. And of course, I assume most of you know the principle of circular economy with the technical cycle and the biological cycle. And while the two previous presentations were mainly about the technical cycle, I will today talk about the biological cycle with the two projects which we carried out at Eindhoven University. So in 2014, we started to research and also to educate about bio-based materials. And obviously, in the construction industry, timber is a well-known and very old and traditional bio-based material, but we are looking into other materials. So we are mainly looking at hemp and flax fibers, which are used in composite materials, and also into mycelium, which are used maybe for insulation purposes. But the project today, or both projects I want to present today, is about the use of natural fibers in composite materials. And that image here shows a pedestrian bridge, which we realized in the year 2016 on our campus at the university. And I just want to go quickly through the design and also realization process of that project. So it is a joint project between Delft University, the Center of Bio-based Expertise, and PSP, the industrial partner. And the whole project was led and coordinated by Eindhoven University. And we also involved a lot of students to help with the project. So we started with a design workshop and had some kind of internal design competition to come to a good and interesting design for the bridge which we wanted to realize. And of course, we also started to look into different materials which might be interesting and possible for applications in the construction industry. So in terms of the fibers, we looked into flax and hemp fibers. So these materials are locally grown and produced and also commercially available in the Netherlands. So that's why we selected them. Then we looked into different kind of resins. So the goal was to use a resin which is 100% bio-based. But unfortunately, at that time and still until now, these materials are not commercially available. So we used Zircomin green epoxy, which is a 56% bio-based resin, which we used in that project. And as the core, we used a bio-based PLA material. So that's a material which is completely compostable, but with the challenge that this material has a melting temperature of approximately 80 degrees Celsius. And the issue here is that during the hardening of the composite material, the temperature can increase above 80 degrees, which of course leads to the melting of the PLA foam, which of course causes problems. So for the production of the bridge, we then added additional cork interlayer as a kind of insulation between the hot composite material under hardening process and the PLA, which was used as a lost formwork. And obviously there are not too many experience in terms of the mechanical properties, in terms of strength and stiffness of the natural fibers compared to other building materials, when normally in construction we are using steel, concrete, etc. And then there's of course a lot of experience in buildings codes, but that's not really available for natural-based fibers. So in our lab, we did a couple of tests with different fiber configurations. So in that table, you can see some of the results. So UD stands for unidirectional fibers. So all the fibers are orientated in one direction. Then we have woven bidirectional fibers. So as the name indicates, the fibers are orientated in two directions, and also non-woven and hybrid materials. And you can see, especially for the UD materials, the strength is actually quite high, so up to 200 megapascal, which is comparable to aluminium and only a little bit less compared to traditional steel. So I think that's very promising from a structural engineering point of view. And even if the bridge was realized on the campus of the university, it's public space and public access, so we had to go through the normal building application procedure. So we had to submit a calculation report or the drawings to the authorities to convince them that the bridge is not only innovative and interesting, but also safe, of course. So based on the Eurocode and the relevant Dutch annexes to the Eurocode, we did the structural engineering and structural design of the bridges using different kind of finite element models where we calculated the stresses and also the deformations of the bridge. And of course, also we used the results of the lab tests in terms of the stiffness of the material as input for the numerical analysis. And the load which we have to apply according to the Eurocode are 5 kilonewtons per square meter, so 500 kilograms per square meter on the bridge deck. And that's what we applied in the numerical test and then also later on in the load test as well. Here you can see the production process on the left side. It's a 1-to-1 scale mock-up. So the green grayish internal stuff, that's the PLA core, which was used as the lost formwork, and the shell structure around it, that's the composite, the bio-based composite material, which is a combination between non-woven and bidirectional woven material, as well as unidirectional materials in the areas where the stresses are the highest. Some more pictures from the production process. So on the left picture, you can see the different layers of the material which were put on each other before we put everything into a foil, and then the resin was sucked into the kind of mold by vacuum infusion. So you can see the yellow pipes. So these are the pipes where the resin is sucked into the with a vacuum into the fiber material, and then after the hardening, then of course, everything becomes a strong structure. And even if we submitted all the calculation report and drawings, etc., to the authorities, and of course they trusted us that the calculations are correct, but we still had to do a load test. So we had to apply 500 kilograms per square meter using this big water tanks. And so we applied the water tanks on the bridge. And on the one hand side, of course, for the authority, it was important to show that the bridge can carry the load. But for us, even more interesting was also do the stresses and strains inside the structure, and also the deflections are comparable to our prediction from the numerical model. And there we had a very good match between the load test in reality and the numerical results from the computer model. So that was quite convincing for us. So after the successful load test, then we just installed the bridge in one piece, as you can see on that picture. And then after the opening event, there's the Glow Festival. So Eindhoven is also the city of light, because it's the headquarter of Philips, the light company. And so once per year, there's a big light festival. And in the first year, so in 2016, our bridge was part of the Glow Festival, and we had different kind of light installation, which were done by one of our architectural colleagues. Also important, in the bridge, we integrated sensors, so fiber optical sensors to measure the strains inside the bridge also over a couple of years. So here you can see the sensor arrangement. So we have two optical sensors on the top deck and two optical sensors at the bottom deck. And there's a possibility to plug in your laptop. So once in a while, the colleagues from the sensor company are coming to our campus and they plug in their computer, and then we have either steel weights or water tanks or students walking over the bridge, and then we can measure the strain and also the deformation of the bridge in real time. And parallel to that, we also did some creep tests in our lab to understand the long-term behavior of that material, because obviously creep is an issue for not only for natural fibers, but for composite materials in general. And then let's come to the second project. So based on this initial project, we submitted an application for a larger European project, a so-called Interreg Northwest Europe project, which is a project with 14 partners from the Netherlands, Belgium, France, and Germany. And in the context of that project, we will design, also realize 3 more pedestrian bridges, all again implemented with the sensors and the health monitoring system to get a better understanding of the long-term behavior and also the impact of environmental effects on the structural behavior over time.
Sorry,
yeah,
Patrick, you have 1 minute.
Yeah, okay.
Yep.
And of course, for the construction industry, and also from the structural engineering point of view, there are a couple of aspects which will be studied in the next 3.5 years: temperature, UV light, moisture. Then we are integrating the structural health monitoring system, and of course, we try to understand the material properties more and better. So on the one hand side, one colleague, one PhD student is looking into different stacking sequences of the different layers in order to optimize the mechanical properties of the materials. Again, for the submission for the authorities, we have to produce a calculation report, not only to check the stresses and deformation, but also the eigenfrequency and vibration potential of the bridge. And another colleague, she's looking into the end-of-life scenario of these composite materials, which of course is important in the context of a circular economy. So we look into mechanical, biological, chemical, or thermal end-of-life scenarios of the composite materials. So, and to conclude, I think there are a couple of benefits which you can read here from bio-based composite materials compared to glass fiber or carbon fiber compared composite materials. But obviously there are also challenges. For instance, the environmental impacts, which need to be studied and will be studied in the coming years. All right, thank you for your attention.
Thank you very much, Patrick. I really want to that COVID ends so I can travel and try to walk over this bridge. Very nice example of doing something the full full way. I think we can squeeze in one question. I was interested in the part because that was my first thought when you started to talk about this, the authorities, because of course from Sweden we often think of them as okay, that's one of the maybe bottlenecks or so, and also an enabler. But was it very hard, and did you have to do very major deviations from Eurocodes in order to convince them?
No, I think in that case it was, then of course it was some effort we had to do the one-to-one scale load test, which of course is some extra effort, but apart from that, I think all the talks and negotiations with the authorities were quite okay. So next year we will also realize a bridge in Germany, and so I'm from Germany personally, so I know that will be more challenging than the Dutch authorities.
Okay.
But we will manage somehow.
Good to hear. Thank you very much. We move on to our fourth talk, I think it is. Yes, it is. And that will be given by Marie-Claude Belland from RISE, another colleague of mine. And the title is Circular Strategies for Bio-Based Composite Materials in 4 Market Segments. And Marie-Claude is Business Development Director in Biorefinery and Energy. So please, Marie-Claude, the stage is yours.
Thank you so much for this introduction, Linus. Just a small remark that Marie-Claude Belland is our project coordinator, and I will be presenting this part of results now. So I hope this is fine with everybody. Yes?
Absolutely.
So,
then you can give some introduction to yourself.
Thank you so much. I'm as excited as Marie-Claude to participate in this conference, and my name is Tatjana Karpenja. I am a sustainability and circularity expert at RISE, Research Institutes of Sweden. So the topic of the presentation is the same, so circular strategies for bio-based composite materials in 4 market segments. So I will start with sharing the screen and actually saying that I'm really impressed of the bridge that Professor Teuffel showed just right now, and it convinces me more and more that the circular economy can be beautiful indeed. So, and now let me put myself in the presentation mode and continue with the presentation. So let me see if you have the screen now. Yeah. So this work has been performed within the Biocomposites project that was financed by the Strategic Innovation Program Bioinnovation. We are totally 24 partners with the common aim of developing new biocomposite materials and also production of demonstrators that represent 4 market segments. So because this project is heavily industry driven, it was very important that the demonstrators are produced at a larger industrial scale, so not at the lab scale. And the additional challenging aspect was the complexity of the requirements set on the performance of these materials. So such as the materials needed to be mechanically strong or lightweight or 3D printable and so on. And in this project, many demonstrators were produced from different biocomposite materials. And here in this presentation, we will focus on 4 of them that are marked here with the bold font. So the composition of each material was a bio-based reinforcement fiber in polymer matrix, which can also be bio-based. So number 1, compression molded furniture made of oat hull. In Swedish, it's havre skal, and cellulose fibers. So oat hull contents in the range of 10 to 60%. And on the picture here, you see the recycling office beans. It's about 30% of the oat hull content. So segment 2, new prosthetics, novel prosthetics consisting of 3D printed blend of microfibrillated cellulose, so MFC, with polypropylene. in the future with a bio-based polymer. And the third market segment is transportation with a vehicle component as a demonstrator, which you see on the top of this slide. And this demonstrator is produced as a high-performance sheet molded compounds that is made of hemicellulose-based furfural alcohol resin and carbon fiber 50-50. And finally, the paper-based bottle made of cellulose fibers with a polymer coating inside. So a kind of composite laminate structure containing 85% of wood fibers. In a separate work package called Circularity and Coordination, so together with Marie-Claude Bieland, we explored circular strategies for these 4 demonstrators made of different materials and located in different market segments. And this we've done by performing a material flow analysis of each demonstrator, so by mapping inputs and outputs of the processes within each demonstrator life cycle. In the next step, by applying the circular strategy framework for exploring the possible end-of-life scenarios. And in particular here, we looked at acquisition step, which is basically collection and sorting, how these products will be collected and sorted. In the next step, it's reprocessing. So will the products or materials be recycled or maybe reused also? And finally, remarketing. So what these products will become in the end of their life cycle. So, and final method we use to iterate the demonstrators through the different circular business models in order to select the most attractive and feasible ones. And business models can be discovered in different parts of the whole life cycle. So from the choice of raw materials until end-of-life options. So this will be the latter. This will be the focus of the presentation from now and on with this explorative method. So the first column here, it shows the list of the main types of business models, or you can say strategies, with their variations, or so-called sub-business models that you see in the second column. In the case of the vehicle component demonstrator, the business models within the sectors 1, so circular supply chain, and sector 5, recovery and recycling, were activated. And in the today's scenario, the vehicle component is made of steel. So the current strategy is built to last, which basically means that the material is durable, and that it is recyclable and will be recycled as the next strategy. So in the new exploratory scenario, the vehicle component is made of the biocomposite material that is also durable, reflective of the vehicle's lifetime. And the circular supplies strategy in our case is about bio-based renewable composite material. Upcycling here means that the material has the potential to be recycled into a higher value application in the next life cycle. And then next, analyzing the prosthetics in the current scenario, this is energy recovery, where the product will be incinerated as mixed waste without any material value recovery. And this is a durable material today. And in the new scenario, biocomposite material is also a durable one, so MFC and polypropylene blend, 3D printed, and the strategies which are relevant is built to last, circular supplies, so a bio-based material again, but also reselling and recycling. So totally 4 different circular strategies. And going further to the furniture market segments, where we have office recycling bin, from energy recovery today to the strategies of circular supplies, so bio-based material, and repair and maintenance possibilities, and also recycling. So 3 standalone circular strategies. Finally, we have the paper-based bottle where we are switching to the bio-based materials, so circular supplies, again, as in all other demonstrator scenarios. And we keep the recycling step, but in this case, it will be paper packaging recycling instead of plastic packaging recycling. And the final part of this circular strategy analysis, it included a deeper dive into the strategy's characteristics, which are incentives and enables, as we've heard a bit in the first presentation during this session. So we had obstacles and promotions. Here we have incentives and enablers of the circular strategies. So this research part is crucially important, since it's about unleashing the main driving forces behind the circular shift, and also understanding how feasible these strategies are, or how not feasible these are. So basically understanding the reasons why going circular, and also how to make it happen. And here the demonstrators were first classified according to their lifespan. So from long time lifetime for the vehicle component in the top row here in the table, to the shortest lifespan for the paper bottle. So then the previously standalone circular strategies, these were put together into meaningful combinations of business models and evaluated. So we take only one example here, office recycling bins, which was assessed to have the potential of becoming circular by two roads. So by combining these circular supplies and repair and maintenance strategies, or by combining the circular supplies and recycling strategies. So both roads are relevant due to strong drive for bio-based materials. So resource efficiency through industrial symbiosis. We have old hull, which is waste normally and is incinerated. So by this, we create value for this material. Another incentive was exciting in terms of material identity, because the material has unusual dotty appearance, creating kind of distinguished aesthetical look that is interesting for designers. And these two roads, though, will have different enablers depending on which strategy you choose. So a modular product design with availability of spare parts are enablers.
Sorry, Tatjana, 1 minute.
Yeah. Mm-hmm. So enablers in one case, and then a separate collection stream with mechanical recycling. These are enablers in the other case. So what we've done, we summarized all the analyzed business models on this circular strategies map for the biocomposites, and you see that you find these strategies along the whole life cycle. So in the beginning, in the design phase, where you choose materials, during the use phase, and after use. So the conclusions are quite straightforward. You can find the value for biocomposite materials on the level of products, components, and materials, which we discovered in this big project. I encourage you always to look at combinations of circular strategies, because this is very powerful and maximizes the circular economy potential. It's important to understand incentives and enablers of your ideas, because when you put together your new cycles, so circular cycles, or you adjust your current ones, this one will be the crucial to lead you through this process, and also finding the right partners for the cooperation. So this is it from us, Marie-Claude and myself. Thank you so much for listening.
Thank you, Tatjana, for giving this presentation on this very interesting research. I was struck, and it was very good and general way to, I guess you can apply it on basically every product. And do you give this as a service for companies, or is it still in the development, this process, let's say?
No, of course, it's a kind of exploratory work. we as RISE researchers together with industry, we gather together and discuss, and we have a specific process for that. So how do you start, how you analyze different aspects in order to get the structured and concrete result, which you can afterwards evaluate if you want in terms of environmental, economical, and other types of impact, if you wish so. Yes.
Thank you. Yeah, we're in good time, and so we skip to next talker. Thank you, Tatjana.
Thank you.
And next time we'll get your name right. So the fifth speaker is Ann-Kristin Jansson, also from RISE, and she will give the talk Resource Efficient Use of Fiber Reinforced Polymers. And Ann-Kristin is a researcher at RISE and working on bioeconomy and health. So, Ann-Kristin, welcome. The floor is yours.
Thank you for the introduction. I hope you can hear me and see me.
Yes.
And let's see if you can see my slides.
Yes, we see it.
Sounds good. Yes, resource efficient use of fiber reinforced polymers. That was also a project founded by the Swedish Strategic Innovation Program Resource. The project partners within this project, apart from RISE, was a number of composite manufacturer. It was ABB, which produces insulators. Podcom, they produces sanitary room products. And Måle Sport Sales, they sell a lot of hockey sticks. And also a recycling company called BDR. And the aim with this project was to build new competence and develop method to enable a more resource efficient use of complex polymers, both glass and carbon fiber reinforced polymers. So this was 2 years, 2-year long project, ended last year. And well, we've been up to composites in previous presentations, but I will just give some short words about the background. These fiber reinforced polymers have a great property in terms of both strength and low weight. So due to that, they've been used in a number of different applications in both transportation and construction industry. And to the right here, you see a graph of the global demand for carbon fiber, and it seems to be increasing quite a lot. So as we've been up to earlier the whole day, efficient reuse and recycling is of great importance. Yeah, the aim is to have an efficient use of both carbon and glass fiber reinforced polymers. And in this project, we have been working both with the reduction of waste, try to reduce the waste within the production facility. We have evaluated the reuse, both in alternative applications and also evaluated different repair processes to be able to use the material for a longer time. And also material recycling. In this project, we have evaluated pyrolysis to be able to recover both the fibers and the polymers. And we have evaluated the products and also produced new composites from the reused fibers. So here to some of the results, a very short sum up of what we have received regarding reduction of waste and reuse. We have managed to reduce the waste within the production facility by 28%, actually, by improved quality management and personal education. We have also reused these polymers in different applications. Everything from furnishing in stables to forecourts and storm water wells. And hockey sticks, we have repaired them and both looked at it theoretically via simulations and also practically with rather good results, at least with regards to the strength. And also we have tried to use these hockey sticks, end-of-life hockey stick, as local reinforcements of steel. I will focus a bit more on the material recycling part of this project. We have used pyrolysis, which is a thermochemical processes where we heat the material for somewhere between 400 to 800 degrees C without adding oxygen. And then we more or less separate the incoming product. We receive the fibers and we also receive pyrolysis vapors. The pyrolysis vapors is then condensed to a liquid, but it could also be a wax for some kind of materials, and the non-condensable gas. And this liquid, it can be used in combustion applications. It can be used to produce fuel, like in conventional refineries, but it's also possible to recover the chemicals within the oil. And the fibers can also be reused in new composites, and this is a picture of a sheet molding compounds. So within this project, we have been working in rather small scale. We started in really small scale, where we analyzed the different materials in analytical scale. So you see here to the left, it's very small scale, it's milligrams. So here we analyze the different material using analytical instruments, the gas chromatograph, to see what type of pyrolysis product that we can receive from this type of process. And what we see here is actually that the products in the pyrolysis oil, you could say, they are very similar to what you put in to producing the composites. So that gives us the possibility that it's actually possible to recover the components in the liquid. We've been going up in scale a bit, been working in lab scale. We actually built a small equipment to be able to treat these these composites. And here to the left, you see how the composites look like from the beginning before we put them in the pyrolyzer. Here's a mass balance over the pyrolysis. So these composites, they compose a lot of fibers, and that's why it's not so, they are not wanted in incinerators, because it produces a lot of ash. But instead, if the fibers can be reused, it's a much better option. And also here we received an oil, and here we were able to quantify it and also to characterize it. And also here we found out that the components we received are actually those, more or less those that are put into the composites from the beginning. We have also characterized the fibers, and as it seems, the mechanical properties are more or less retained after the pyrolysis process. Here we have a carbon fiber reference, and we have tested the strength and modulus, and then we have compared that to the pyrolyzed and incinerated fibers, and it's more or less in the same range at least. And from this recycled fibers, we've also produced sheet molding compounds. And we have also tested that mechanically. And what we see is that the mechanical properties are more or less the same with both pyrolyzed and incinerated fibers. So if we come to the conclusion then, to enable a resource-efficient use of fiber-reinforced polymer, the entire life cycle from use, reuse, and recycling must work. And as we've talked about earlier today as well, it requires a collaboration between the entire chain, from manufacturer to end users. And reduction of production waste together with reuse, and also can effectively improve the resource efficiency, while the inevitable waste can be efficiently recycled via pyrolysis and reused in new composites. So yeah, the recycling is of great importance and interest from the composite companies. And well, we're verified that this works in a rather small scale. So now we want to go up in scale and show that it works also in larger scale. So thanks for me.
Thank you very much, Ann-Kristin. Very interesting. Now I realize I think I got the answer already on one of my questions when you showed that you have used hockey stick as local reinforcement.
Yeah.
Still, I guess you meant that you had pyrolyzed it and made these fibers.
Actually, this was not within the material recycling, but then we used the hockey sticks to do a new product. So we improved the strength in a new product using old hockey sticks.
Okay. Interesting. You also showed some mechanical strength parameters for these composite materials, I think, in the last. To put them in a context for someone who is not used to these materials, what type of applications do that fit? Meaning requirements from different producers and industry. Does it fit a large spectrum of what is requested, or do you know that?
I'm actually not this composite person. Maybe someone else within RISE can answer that question. I'm more into this recycling area.
Okay, but then you can get a question in that instead. And maybe we can leave to someone, if someone is online maybe, and give in the chat. You mentioned the upscaling, which is also very interesting. And you said that you had taken some steps toward that, or is that
we actually this project ended last year, and we have started a new project also, where we are building a larger pyrolysis plant and are able to produce more fibers and more oil to be able to do something more, to be able to produce more prototypes as well. Okay. So the project is going forward, even though this project stopped.
Okay, thank you. So maybe next year at next CRM conference,
maybe
we will hear something new. CMR, I mean. Okay, I think we thank you very much, Ann-Kristin, and we go to the last speaker. And that's Lena Smuk from RISE. Lena is a researcher at RISE, and the title of the presentation is Future of Fiber Reinforced Plastics Composites, Enabling Materials Sustainable Value Cycles. So welcome, Lena.
Thank you. And I hope you see the presentation now.
Now I see it, yes.
Yeah. So good afternoon, everyone, and I will be happy to tell you a little more about our work on making use of fiber reinforced plastic composites resource efficient and creating circular flows. Little different aspects from what Ann-Christine was talking about. A big part of what I will be telling you is based on the results from a project financed by Resource, where we gathered quite strong industrial consortium to look at different system aspects of creating circular flows of fiber reinforced plastics, and look at current situation, at anticipated future situation, at what flows are important, how they differ from each other, etc. So when talking about material and market trends, I suspect I will not tell you very much new. It's quite obvious that use of carbon fiber reinforced plastic composites is growing very much, and this is due to ever higher requirements to the performance of these materials, and where carbon fiber is actually needed. At the same time, thermoplastic-based composites are also growing in use, and this is both due to the mass production that is needed for new applications and very high interest to these materials, but also because recyclability of composites is of high importance for industry, and thermoplastic is one way to get to recyclable composites. 3D printing is very hot topic, and this is again because new applications are of interest, and because people want to make them available everywhere. Also, bio-based composites are of high importance now, and the development is ongoing very actively. And finally, it's interesting that automotive is definitely leading the growth in use of carbon fiber reinforced plastics because of their excellent properties, and because they strive to reach higher and higher fuel efficiency. What is interesting is that in actually the history of use of fiber reinforced plastics in the automotive is much longer than you can imagine. It was as long time ago as 1953, then fully composite car body was built and was produced in quite big amounts during whole 10 years almost. And since then it's used all the time in different parts, not probably the whole car body, but now, as said, the use of both carbon fibers but also glass fiber composites is growing very much in the car industry. But still, the real breakthrough in use of composites is anticipated when we come to the situation when we stop building cars to be safe to crash, when we start building cars that never crash, when people will not be involved in driving cars, and they will be fully automated, etc. To make wide use of composite materials in the automotive possible, they need constantly to fight against the price rise here, because for now the situation looks as follows. You can save 50% of weight when you substitute the traditional metallic part with the carbon fiber reinforced part, but the price raise will be 570%. So this is quite big, and the automotive industry makes all possible. They use discontinuous and continuous fibers and thermoplastic and thermoset matrices, and they try to combine different parts to reach the required properties and to lower the price somehow. As for the trends in the wind power, they're very simple and understandable. They're growing in size, they become larger and larger, and with such huge long blades, carbon fiber becomes vital, because only with carbon fiber you can reach the required mechanical properties. At the same time, wind power industry is very concerned about recyclability of their blades, and that's why very active development of thermoplastics based turbine blades is ongoing everywhere. Bio-based composite materials also of high interest, but thermoplastics, this development with thermoplastics is much more successful at the moment. With the construction industry is probably the newest among those big users of composite materials, but they really come to the market and come very powerfully, and are used in large amounts now, not only in disaster-proof buildings or exotic projects, but in usual projects, usual buildings, and this is really seen as a material of the future in the construction industry. So what have we found out in our study? Actually, as said, we looked at mainly focused on 4 different flows, and this is from automotive, from wind power, from consumer goods, let's say sport equipment, which almost all is made of composites at the moment, and the construction industry. And we found out that these flows, they have problems linked to different places in the life cycle, and potential high impact actions can be taken in different places of life cycle. For example, if we are talking about the collection and end of life situation for different flows, we can state that only wind power has such a controlled collection, which means that when you know what you're collecting and when it ends up, and there is a linked logistics to that. With the automotive, unfortunately, this is not the case. Those composite parts, they go to shredder together with everything else, and no one actually knows where they end up after the shredder. They are not detectable at the moment in other flows. This is due to quite low amount, probably because these are older cars with lower amount of composites used. But it's quite clear that it will change one day, and that's why it's very interesting research question linked to that. What is this critical amount that will affect the recycling of other flows, and where actually they end up for the moment? With the consumer goods, the situation is even more interesting. It's almost detective work, which is in front of us. Because the situation with reuse of, for example, sport equipment is very good. These are fancy and expensive parts, expensive products that are resold many times and reused. But when you cannot use them anymore, no one knows where they end up. There is no any dedicated collection of this. So they end up in incineration, most probably in other flows, and contaminating other flows. And this is partially linked to very low awareness of both consumers and a large part of waste management system about such materials as composites and why they're different. When we talk about reuse, as said, reuse of consumer goods looks good. Actually, reuse of wind power also looks good, because there is quite developed market for second-hand market for this. For construction industry, it's not relevant because they are just starting and they have very long service life. So the most relevant this question is for the automotive industry. Even though the cars have quite long service life, those composite parts they have the same quality, preserve their properties for much longer, maybe 50 years. So they, from technical point of view, they should and can be reused again and again. And though it can sound quite crazy for car manufacturers at the moment to reuse, but to reuse something in new cars. But with the changing paradigm, with changing business models, and with our move to circular economy, when with all this car sharing and selling services instead of selling new fancy cars, and with the car manufacturing is trying to modularize structures, so the same modules would fit different models of their cars. This will become the reality. We are absolutely convinced. So this is very interesting to see what technical, economic, and organizational conditions are needed to make it work. When talking about mechanical material reuse and mechanical recycling, then of course wind power has the largest potential, and this is developing very fast, and because of a set controlled collection and linked logistics to that, but also because they can provide large amounts of material of consistent quality. One interesting aspect here is that even though such large amounts of consistent quality can be provided, there is no any continuous supply of this material. So we see it interesting that there is probably a room for one new player in the market, someone who will take care about creating this continuous supply together with all specifications, etc.
Sorry, Lena, 1 minute.
Yes. I'm finishing. So in manufacturing from recycled, the situation is very similar to all other materials on any market, and probably legislative changes are needed to facilitate this process. And not finally. When talking about creating really circular flow, we come to the aspects that Ann-Christine was talking about, and this is chemical thermochemical recycling, which of course is the key. With the composites, technical development is needed to make it possible to recover high quality hydrocarbons while keeping quality of fibers high, but also some fundamental changes, I don't know, with the help of legislation or something is needed for making it work economically for glass fibers specifically, because they are so cheap now that any cost of recycling make it completely impossible economically. And finally, when talking about use phase, here construction industry comes into the picture. They are new users, and it's very important that they use all possible traceability instruments to make it possible that all information follows along the life of these products to the recycling system. And also it's important, as I said, to raise awareness of these materials among consumers and among waste management system. This is the first important step to make collection and processing of these materials separate possible. We are still working on these system aspects, and now we are working on creating a European proposal regarding these questions and some other research questions. And we have gathered already quite strong consortium, but if you are interested, if you think that you can contribute, please contact me and we will be happy to discuss possible collaboration. Thank you.
Thank you, Lena. Very interesting and nice to see that also project bear fruit in a continuation. So I'm very wish you luck with this application. I think we can squeeze in one question, and actually it's concerning this, what you talked about, the windmill wings. I'm actually a bit curious, what is the service life and why do they degrade in the first place? So you need to reuse them, because in my simplistic, naive world, you build a windcraft mill and then the real
situation, yes, the real situation is that why second-hand market exists, for example, is because they are taken off earlier than they degrade, and this is because of legislation. Legislation is created in such a way that you get support during some time, first years of its use, and then it's not economical for you. You stop getting this support. So at this moment, Western Europe usually takes down this old turbine and sells it further. Why they degrade? This is a different question. They degrade because of huge load that those blades have. They are spinning very, very fast. Actually, the linear speed is absolutely huge, and that's why, of course, it's quite big load, and any material would degrade. And they degrade not very fast, but still, this is natural process, and everything else. Well, actually, the service life, or expected service life, is 25 or 30 years, and probably they serve such long time on the second-hand market, but they're usually taken from the use much earlier, as said, because of legislation.
Oh, okay, interesting. Thank you very much. I see that it's now 4:15 and it's time to wrap up this session. I will not say too much, just to thank all of you 6 presentations, and it has been an honor to be moderating this session and hear all your very interesting talks. So with that, I think we close this session, and hope you have a very nice and pleasant afternoon. Thanks.